So we're in chapter 9 now. I'm going to go over chapter 9. This is the homework for chapter 9, homework 10. Let's look at the PowerPoint presentation. And here it is. Actually, let's get to... So chapter 9 is different in that this is pure chemistry. So we're actually getting into chemistry. We're not going to go too far into chemistry, actually. This is kind of an intro to chemistry. This is an important concept, the idea of a molecule. So it's the smallest particle that still retains the characteristic chemical properties of a substance. That's an important definition, and I think we should definitely know that. That's a central idea. In chemistry, the chemists always like to think of things as molecules, even if it's a single atom, like a helium atom. They would just call that a monatomic, mon meaning one. Here's two oxygen atoms bonded together, also known as O2, and that is actually what we breathe when we keeps us alive, the O2 molecule. Here's a triatomic molecule. There's three atoms of oxygen bonded together, also known as O3. This has another name called ozone. And then there's two hydrogen atoms bonded together in a diatomic form. So diatomic is just two atoms, triatomic three, monatomic it would just be one. Alright, so let's move on. So really the important thing is the definition of what a molecule is. Alright, so we have chemical reactions, we have reactants, generally on the left-hand side, going to products on the right-hand side. So this is just a pictorial. We'll actually get into chemical reactions in the next chapter, chapter 10. So valence electrons, so the thing about this, and I did mention this in chapter 8, is that the outer electrons determine the chemical properties of an atom. That's very important to understand. So for example, you take sodium. Sodium has one outer electron in its third shell, as it shows here. It's the 3s1 electron, if you remember your electron configuration. And so what sodium does best is to lose this electron. In fact, all metals, sodium is a metal. Of course, it's on the right, so it's the left-hand side of the periodic table, and so all metals tend to lose electrons, and when they do, they become positively charged. And so notice we have the sodium. This now becomes what's called an ion because it's charged. Okay, so non-metals tend to gain electrons, and they'll like fluorine, for example, will gain one electron and will be a negative ion. All right, so if you look at the electron configuration of the sodium ion, once it's lost that one electron, it actually looks identical to the neon atom. And neon is in the last group of the periodic table. Let me show you that real quick. Anyhow, actually, before I do that, let's talk about the octet rule. So here's what it says. It says atoms attempt to acquire an outer shell of 8 electrons. Electrons can be gained. Those are the non-metals. They can be lost. Those are the metals, or they can be shared. Generally, the sharing happens between non-metals. So right now, let's take a quick look at the periodic table, which you notice I've included this periodic table plus the table of polyatomic ions here, and let me switch to that real quick. So that here's the table of polyatomic ions, table 9.2, and we also need table 9.3. I'll get to those in just a little bit. And then we have the periodic table. You might want to, print this out, and I know it's sideways, but print it out, and you can use this to do the homework. Or it's actually this periodic table is in the back of the the back of the book, the back cover of the book. Okay, so notice this first column. I know we're looking at it sideways. I'll get another view of it in a little bit. Anyhow, this first column, which includes, of course, sodium and potassium and lithium and hydrogen, and all of these act the same way. They're going to lose one electron. Those, remember, are the alkali metals. The alkaline earth metals is column 2, and they always lose 2 electrons: beryllium, magnesium, calcium, strontium, and barium. Okay. Then these here are the transition metals, and that's, in fact, that's where we're gonna go back up here when we start talking about transition metals, or another way they're known is variable charge ions. There's actually some exceptions, even though they're part of the within the transition metals. There's some that don't vary at all. Silver is an example, so is cadmium and zinc, and also tungsten. In fact, if you look at the top of this table 9.2, it shows zinc, tungsten, silver, and cadmium have these charges, which are indicated. Like, for example, zinc it loses 2 electrons, so it's +2, but it always does that. So does tungsten. Tungsten always becomes +6. Silver always becomes +1. Cadmium always becomes +2. Now, but those are exceptions. Those 4 are the exceptions in these transition metals. So even though they're part of this group that we call transition metals, they lose a fixed number of electrons. They never vary. Okay. And then over here, of course, after the jagged line, we have the nonmetals. This 7th column these are called the halogens. They like to gain 1 electron because look what happens. If fluorine gains 1 electron, it looks like neon. Chlorine gains 1 electron, it looks like argon, and so forth. Bromine gains 1 electron, and it looks like krypton. And iodine, same thing. If it gains 1 electron, it looks like xenon. And so all these down here have 8 outer electrons. Notice there is one exception. That is, of course, helium. But the only one in that row, of course, is hydrogen. So helium and hydrogen. Hydrogen can either lose an electron, which would make it acting like a metal, or it can actually gain an electron. And if it gains an electron, it looks like helium. So its outer configuration is just 2 electrons, and it usually does so by sharing an electron with another atom. But yeah, hydrogen would be the only exception to what's called the octet rule, because there's no way for hydrogen to have 8 electrons, but it can act like it's having 2 electrons. Okay, so all right, so let's continue here. I've already gone through this. The sodium ion looks like neon, and so it's met its octet rule. Remember, there's only one exception, and that is hydrogen, which can only have either no electrons, it's lost an electron acting like a metal, or it's gained another electron, and so it's going to be -2. All right. So there are 3 types of bonds. These are electrical forces that hold atoms together. There's ionic bonds. There are covalent bonds. Ionic bonds are primarily between metals and nonmetals. In chemistry, there's sometimes exceptions. Just like when covalent bonds are primarily between nonmetals and nonmetals. And then metallic bonds, I think is pretty obvious, are between metals and metals. We're really not going to explore metallic bonds at all. We're going to primarily concentrate on ionic bonds and covalent bonds, and really just naming them, right? So covalent is the right-hand side of the periodic table. That's what that means. So between two nonmetals, primarily, as I said, there are exceptions, but we will stick with almost exclusively with non-metal to non-metal, and for ionic bonds it's going to be metal and non-metal. So here's a primary example, a beautiful example, in fact, of an ionic bond. So you take sodium. Let me get a periodic table. All right, this is actually from the Chapter 8 PowerPoint. So of course, these are the metals, including these two, the actinide series and the lanthanide series, which are also metals. So all of these are metals. Then you get to this jagged line, right? The stuff right along the jagged line, silicon, germanium, and arsenic primarily, are called the, sometimes they're called metalloids. They're also known as semiconductors. And then up here we have, on the right hand side, these are all the non-metals. So once again, and you got to try to remember this, because it's the first thing in naming molecules. So that's primarily what we're going to be doing. I haven't really said that yet, but that's primarily the big thing that we're going to do, is name molecules. So one of the first things we have to identify is whether it's an ionic bond, that is one of these metals with one of these nonmetals, or a covalent bond where it's a nonmetal with a nonmetal. Okay, so metal with a nonmetal, ionic, nonmetal with itself or one of the other nonmetals is covalent. Again, there are exceptions. There are situations where you can have, one of these metals with a nonmetal, and that would still be a covalent bond. But we're going to try to stay away from that. Okay, so here, let's go back to the other. All right, so I'll switch back and forth. That way we can actually see these. So right away we see sodium and chlorine. Sodium is a metal. Chlorine is a nonmetal. This is a group 1. This is a group 7. So that's clearly an ionic bond. And so there's actually several ways to figure this out. But one of the easiest things to do is to just say, well, sodium's is in group 1, so it's going to lose one electron, so it's going to be positively charged. And then chlorine is from group 7, so it needs one more electron to meet its octet rule. And the sodium is positive, the chlorine will be charged negatively, and so then they'll stick together. And it's a 1-to-1 relationship, 1 sodium for 1 chlorine. Okay. So I'm going to do this with the dot structure from the last chapter that we learned. Of course, sodium, to meet its octet rule, it's going to lose 1 electron, so it becomes charge plus 1, right? Because now 1 electron is missing. For chlorine, because it's a halogen. And the way that you can always do the nonmetals is it's just 8 minus the column number. Okay, so here let's go back and take a quick look at that before. Oops, there it is down here. So the column number is 7. So 8. Well, let's do this. Let's say the column number minus 8. So since chlorine is in group 7. So see there's the Roman numeral 7. Then 7 minus 8, of course, is minus 1. So let's say we had oxygen, for example. So it's going to be group 6. So 6 minus 8 would be minus 2. So oxygen and sulfur here are minus 2. Similarly, nitrogen, which is a group 5, 5 minus 8 would be minus 3. And then the last one, of course, would be carbon, which would be -4. All right, so let's go back